Continuing with some of the basic concepts in algebra as we continue topic 2 of chapter 1. Now the topics to be covered are quite extensive, and a lot of basic concepts in algebra will be reviewed. Take good notes. This section deals with properties of exponents and radicals. So we'll jump right in here. I think you're basically familiar with what exponents are. And just to review, we have a base, let's say the letter A, and we have an exponent, which is like 3. And this is a shortcut for writing that this base A is multiplied by itself 3 times. Now, every variable and every number itself has an exponent. Even if it's not written, there's always a 1 there. Okay, let's go on. Looking at background, if we have a square whose sides are equal, the formula for area is area equals, if it's a square, it would just be the sides squared, so a squared. Now for the volume, where it'd be 3 sides, this times this times this, the area of a volume is a to the third. So again, where we're using exponents in calculations. So now in your notes, example 1, and I'll go to a finer pen here, stylus. What does 4 to the third power give you? Well, 64. Now here in letter B, our base now is 3, a negative 3 that's squared. So this would be a negative 3 times a negative 3. Negative times negative gives you a positive 9. Now a little thumbs up is if we're raising a base that is negative to an even power, our answer will always be positive. If we're raising a base to a third power, which is odd, or fifth, or seventh, our answer will end up being negative. Now, letter C is kind of interesting in that it's a negative 3 raised to the fourth, but what is my base here? Is it the negative 3 as it was above, or is it just the 3? And the answer is it's just the 3. The exponent applies only what's to its immediate left. That's the base. So the base is not, as we see here because of the parentheses, a negative 3. So this answer is going to be negative. And we sometimes can think of like a negative 1 times that. So again, you needs to be careful about this. And 3 to the fourth is 81. Okay, and they're reviewing what we just said here. All right, let's look at item D. Here we need to be familiar with the order of operations. What do we do first? Well, we would do what's in the parentheses first here. So this is a negative 2 to the third power, which becomes a negative 8. That's what would be in the parentheses, but there's a negative in front of that, so that this part eventually becomes a positive 8. And then it's times 5 to the second, which is 25. So 8 times 25 is a positive 200. In our last example here, example F, we see a fraction And if we were to write it out, it looks like this, and we could cancel out the 1, 7 divided by 7, and we get 7 to the second, in a sense, left, which is 49. One of the rules we'll see shortly that we use for dividing, called the quotient rule, is we bring the 4 across the division bar, the sign of the exponent changes, and we then get 7 to the second. And that's a rule you may recall from earlier classes. Now, we're going to go over these rules shortly, and let's just raise this up a little bit. I want to go over the zero exponent rule, that if we had, let's say, a to the third divided by a to the third, and we're using our rule of bringing this exponent up, it changes its sign, we then would get a to the 0 power, and then thinking of this in its original form, a to the third divided by a to the third, or just plain a divided by a, anything divided by itself, so long as it's not a 0, is 1. So anything to the 0 power, that's the zero exponent rule, is going to be 1. Okay. And they're introducing this little by little, but let's get to, and this next rule is the negative exponent rule. So if we have a to the negative 1, to make that positive, it would be 1, bring it down, and this is over 1, to the denominator as a to the first, and we don't write that. So they're describing it here as a to the negative n equals 1 over, bringing it down to the denominator, a to the positive n. All right, we're going to have now as we do example 2, there's our basic example. Two things can happen. If we want everything in the numerator, we bring up the 7, that becomes a negative 7. So we end up with y to the negative 5th. But if we want this to be positive, we would leave the 1 up in the numerator, bring the 2 down, and then that would be minus 2 in the denominator, and we would get y to the 5th, 1 over y to the 5th. Often they want you to have a positive exponent as a result of your simplification. All right, let's do letter B while we're here. We have a 6x squared over a negative 3x squared. Well, this becomes x to the 0 power, which is 1, or anything divided by itself, since these are factors. This is a 1, and 6 divided by a negative 3 is a negative 2. And that's what we see here. And for this one, let me write it bigger, 5 to the 0 power times 5 to the negative 3 power. Well, this is a 1. So in a sense, all that this is 5 to the negative 3, which we then bring down to our denominator, 5 to the third, which is 1 over 125. And writing example D larger, they go through a longer way. Just bring this negative exponent up, and that becomes t to the third. Now here, this is written, as I show you down here 3 times, keeping in mind there's a 1 there. So we could use the powers rule that we'll state here shortly. X to the second times 3 will be x to the 6th. Y to the first times 3 is y to the third, as we see there. Okay, here are the rules, in a sense, summarized that we've been mentioning here. We finally got to them. So this is called the product rule, where our bases are the same. We just add, and we're multiplying, we add the exponents. Now this is the quotient rule, in which we are dividing. The bases again are the same. So we're just going to subtract the smaller from the larger, and depending if we want to keep our exponents positive or not, some may go down, some may go up. All right, this is the negative exponent rule, that if it's negative in the numerator, moving it down to the denominator, we just change the sign of the exponent. Now, number 4 is the powers rule, where we're raising a base to a power, we multiply. And this is another version of it, keeping in mind there's a 1 by each of the exponents that we need to multiply. And this is just a kind of quotient rule also, to the power that the exponent applies to both the numerator and denominator. And we should add here the zero exponent rule, where any base to the zero power is 1. Okay, you're going to have to pause probably to do this. Now for example 3, again, because of the parentheses, this is raised to the zero power. Anything to the zero power is 1. Now for letter B, this takes a little bit of calculating. So the first thing I'm going to do is take this, which is a negative exponent, and bring it down to our denominator where it becomes positive. Now this is a negative exponent, and this is a negative exponent here. And to simplify this, I'm going to bring the negative 3 up, and I have a negative 2 plus 3 gives me a z that's going to be on top. So the z's are gone now, and I still have the x to the third in the denominator, which I will now simplify to z all by itself in my numerator. X to the second, x to the third gives me x to the fifth, and then y to the third. Taking a little bit of calculation here, and I will raise it up so you can actually see the answer of how they're working it out down below here. And there it is there. All right, let's do example 3 now, or C, I should say. Okay, as we look at it, all of this is going to go to the denominator as a negative 2, x to the third, y to the negative 1, but now raised to the third. Now this is something to the zero power, so this is just a 1. And I'm going to take this and move it to the numerator as xy to the second power. So that might be a little easier to work here. So as we start to simplify, this is going to be x squared, y squared. Now, a negative 2 raised to the third power is a negative 8. This becomes x to the ninth, and this becomes y to the negative 3. So now we can do some simplifying. I have, let's see, I'm going to bring this y to the negative 3 up here, and it becomes y to the fifth in the denominator. I'm going to bring this x to the second down. I subtract it from the 9, gives me a 7, so this is going to be 8 x to the seventh. And there we have it here. All right, let's do that last one. So I started this here. I took this and wrote it on top, but since this is a negative exponent, I just brought it down to our denominator. So now we're going to square this 7, gives me 49. Remember, there's a 1 there. So this will be x to the second, z to the negative 4, all over 5x squared y. And now to summarize this, x to the second over x to the second, this is going to become a 1. So I'm left with a 49 in the numerator. Bring that negative 4 down as y stays there, and then z to the fourth. Okay. Again, seeing it done hopefully is helpful. I'm going a little fast because he's covering lots of material. Now, a nice thing about this is they're showing you incorrect statements and what the correct statement would be. So notice what's here and pause. Take time to look at this. You don't have to take notes on this. Now, dealing with exponents, one of the types of notation often included is what we call scientific notation. And what is that? Well, it's some number between 1 and 10 times 10 to some exponent. This is the form of scientific notation. So putting a number between 1 and 10 and then having it to some power. Now, if your powers are negative, these are going to be small numbers, decimals. If the numbers are positive, the exponents are positive, these are large numbers. And they're mentioning that below here. All right, let's go on. Now, in example 4, they're telling of the distance the Earth is from the Sun, 93 million miles. Put that in scientific notation. So we want our decimal points here, and we want a value times 10 to some exponent. So if it's a large number, we're going to move the decimal to the left so that we make this a number between 1 and 10. So 1, 2, 3, 4, 5, 6, 7. So our number is 9.3. That's what we put here, 9.3. And since the zeros are not significant digits, in this condition, we don't add any more. And how many places do we move it over? 7. So scientific notation for 93 million miles is this. And here, this is really, really tiny. How they ever figured it out, I don't know. But the mass of an electron in kilograms is approximately this. So again, we'll just leave that there. And we count until we get to a number between 1 and 10. So that's going to be 9.11 times 10. And how many decimal places did we move it over? Well, they're saying it was 31. But since it was to the right, small numbers, it's going to be a negative exponent. And that's what we see here. Now for item C, they're talking about the speed of light as meters per second. What would that look like if we write it out here? And the answer would be 3 times 10 to the 8th So we need to have 8 decimal places. So that would be 3. And then we're going to add, not decimals, but places, 8 zeros. 1, 2, 3, 5, 6, 7, 8. So making that easier to read, 300 million. Wow. The speed of light is fast. Now for example 5, I'm going to go right to the example number here. And as we see it, we're going to multiply this part by this part, which I'm indicating here. And we multiply this part by this part, where we just do the subtraction of the exponents. So a negative 12 and a positive 4 gives me a negative 8. So this is what my top line simplifies to. Now the bottom line I just left the same. Now we're going to do this calculation. 3.6 times a negative 6. This gives me a negative value. Divided by 1.8. That's going to give me eventually a negative 12. And then when I bring my negative 6 up, it now becomes a positive 6 that I'm going to subtract 8 from, leaves me with a negative 2. So when I then put this in there, I'm going to convert my answer. Let me show you what the answer would be here. And I had to use my calculator for this. I ended up with a negative 12, and again, times 10 to the negative 2. But this is in sort of in scientific notation. But anyway, keeping in mind our decimal point is here, and I need 2 decimal points in my answer. So I had to move it over this way, and then I get what my final answer is. So again, lots of stuff going on here, and you really need to have a protocol to solve it. All right, let's go on to our next item, on to letter B, and let's see if we can follow what's written. So take a moment to copy it down. Now we're going to multiply the 7 times 3 and get here a 21. Our bottom is going to be 6. And then we add our exponents together and then bring this up, and this becomes positive. So we end up with this times 10 to the 29th power, adding it all here. This becomes 3.5 or 7 thirds, 3.5 times 10 to the 29th. Wow. Okay, but you'll have some practice with this and hopefully a review. Now we're going to do a little bit of review on geometric formulas. Let's take a look at this here. Now the first one is the surface area of a box. So a box we know has 6 sides. So we're going to have 2 tops, which is a top and a bottom, which would be the same, front and back, and then the 2 sides. So putting that all together, we get the surface area. Let's just write this big here. Surface area equals 2 length times widths for, let's say, the top, 2 length times heights for the sides, one of the set of sides, and 2 heights by widths for the other. So again, if you know the values, it just would be a matter of substitution to find out what these would be. All right, they're going to get a little more complex here as we go on. Now this is for a cylinder. And the surface area of a cylinder, again, we have a circle that's involved. So we've got the surface, which is area of the top, area of the bottom is 2 circles pi r squared. And then if you open it up, you get the circumference, which is the radius times the height. So again, figuring it out, but we don't want to spend too much time on this. And then the last one is the volume of a sphere eventually becomes this, and they're showing you the details. And there's one more. So there it is right there. Let's see if we bring it up. Okay. This is sort of a trapezoid in a solid form. And the volume of this could be this formula, where there's the height. You have the area of the top, the area of the bottom, and then the sides, the lengths, and various things. Or it could be written this way if we divide everything by 2 here. So to solve this, I would get rid of the fraction and do twice the volume equals that. Again, you'll have some practice perhaps and some certify on that. Now we're going to get some background information on what we call radical notation. And from an earlier course, you may remember this is the radical sign. What goes in this little notch here is the index. If no number is written there, there is an assumed 2 there. And what goes under the radical sign is called the radicand. Now this is radical form. It also relates to exponential form. Let me give you an example down here, and this is what they're talking about. So if I have the square root, or let's say the cube root of 8, this would be its radical form. Well, this can be converted to exponential form. So the radicand would become the base, which is 8. The exponent, unwritten 1, becomes the numerator of our fractional exponent, and the index number becomes the denominator of that fraction. So this would be radical form. This would be fractional exponential form. That's a good little tool to keep in mind as we move forward here. Continuing on that page, we see perfect powers. Well, what's a perfect square? Well, 1, 4, 9, 16. Just take your prime numbers and 1, 2, 3, 4, 5, your natural numbers, and square them. Now, keeping in mind, those could also have been negative numbers. Negative 1 times negative 1 is a positive 1. Negative 2 times negative 2 is a positive 4. Kind of keep that in mind. And then perfect cubes would be numbers that are 2 times 2 times 2, which is 8. 3 times 3 times 3, which is 27. Keeping in mind you can also have 1. 1 times 1 times 1 is 1. Okay, let's go on. All right, a moment for this, a little flashback in history. Where does the radical sign come from? Well, it may have been tied into the Latin word for root, which is radix, with the R indicating, this sort of looks like an R, doesn't it? All right. Anyway, it was made popular by other mathematicians, and Rene Descartes was one that was famous for it too. We'll be studying some of his work a little later. Let's go on. Now, the proof of the pudding for all of this is to be able to use these bits of mathematical background to solve and simplify. So to keep it a little bit easy here, let's do this one, the fifth root of a negative 32. Now, if this were an even index number, you can't have an even index number have a negative value under the radical sign. This would not be a real number, but having a negative value for an odd index number is okay. And this is a negative 2 to the fifth power, converting that. And the answer would be negative 2. All right, going on to this one. Now here, it's an even number index 4 and a negative. So this is not a real number. And this one now with the negative sign outside, when we take the fourth root of 16, remember this could be 16 to the 1/4 power. Put that in your calculator, you see that it's 2. And then we apply that, remember, like a 1, negative 1 times this makes this a negative 2. All right, we'll unclutter that. In letter D, the square root of 0 is 0. And for letter E, now they're saying the square root of 1 to any, or the whatever n index number value is always 1. Now here, let's write this one big here. It's the third root of, and you can do it this way too, a negative 27 over the third root of 64. And then now, since this is an odd index number, this is okay. This would be a negative 3, and this one would be a 4, which is what they're showing here. All right, here we're looking at pi, it looks like, or any letter. When we do it, if we convert that to its fractional form, this would be a negative pi, or n, to the 5 over 5. Well, this just makes this a negative pi to the first power that we don't write. And that's what they're showing here. Okay, for letter H. Now, as we do letter H, notice we could do this also, negative 3 to the 4 over 4, which would make this a negative 3. Now, also, if we did this, this would end up being 4 to the 81st power. So that would give us then a 3. So you could have a negative 3, or you could have a 3 as an answer for this. So to ensure that you're going to get a correct value for this, they often would put that in the absolute power, which is what they're showing down here. So again, some interesting things, and you'll be tested on this in a sense in your practice and certification. Let's go on. So in example 8 now, we're using some of the things we've had, and I went too far. Let's go. Looking at this, this is the length of one of the sides of the triangle, the hypotenuse, using the Pythagorean theorem. So first of all, what is the radicand here? Well, it's what is under the radical sign, this. What is the index? Well, the index would be a 2 that we don't write there. And that if the values of C, what is the value of C if A is 5 and B is 12? And then if A is 1 and B is 2. Well, they work it out here. It's just a matter of substitution. Remember, you do the parentheses first. This becomes 69. So that one would be 13. This one, when we added it up, would become the square root of 5. Now, one of the things they're not showing you here, which I thought was always a good thing to know, is if we had a square, and I'll make a little square here, and copy this in your notes. And the length is 1 for all the sides here. What is the length of this diagonal? Well, we can use the Pythagorean theorem for that. So c squared equals a squared plus b squared. Take the square root of that, take the square root of that. This then just becomes c, which is where they get this from. But what does c equal then? Well, 1 squared is 1. The other side is 1 squared is 1. So we get c, the diagonal, is the square root of 2. So if you ever want a good definition of what is the square root of 2, it's the diagonal of a square whose sides are 1. And that's a little thing we picked up and adding my 2 cents in a sense. So again, we're going for some more background information on simplifying and combining radical expressions. Well, this is a radical expression. Is it a simplified form? And the answer is no. For instance, you can't have a radical in the denominator. And under the radical sign, you can't have any perfect square factors. So this is what they're reviewing here. So we would tease this top apart into the square root of 4, which is a perfect square, and the square root of 3. And this would be over the square root of 2. Now, when we simplified this, this would be then 2, the square root of 3, over the square root of 2. We still have a radical in our denominator. So very shortly, we're going to show you how to get rid of that radical by multiplying a fraction by 1 in the form of the square root of 2 over the square root of 2, which will now make my numerator 2, the square root of 6 over 2. Square root of 2 times the square root of 2 is the square root of 4. Square root of 4 is 2. And then now to simplify, these 2 would cancel out, and there is what our answer is. Now another way could have been, here's the square root of 12 over the square root of 2, put it under a common one, and just do the division here, and that would be the square root of 6. Comes out either way, but reviewing the items of what is a simplified form of a radical expression. Going on to example 9 now and reviewing. Here's our example that I've written big, and we want to simplify it. So what you want to put under the first radical sign are all perfect cubes. So what would be a perfect cube of 16? Well, we could put in there a negative 8, and we would be left with a 2 over on that side. Now, what's a perfect cube of x to the 8th? Well, the smallest one would be x to the 6th. That would be a perfect cube. And you would have x to the 2nd left over. And for y to the 4th would be y to the 3rd with a y left over. So now these are all perfect cubes, which will become then a negative 2. And you could divide this 3 into the 6 and get 2. and here it's just plain 1. And then the third root of 2x squared y. And I believe that is the answer. For letter B, this is sort of an easy one here, using that technique of what's the largest perfect square factor of 8? And that would be 4, and then a 2, and then z to the 6 is a perfect square. So then we end up with 2 z to the third, the square root of 2. Now, here, if you put that in there, they may not accept that, because what values of z, to ensure that we would get possibly negative values, we have to put that in the absolute value sign that they're picking up here. And you don't need to include the 2. Okay, that looks good. Now let's go on to letter C. Looking at this, and I separated, which we're perfectly qualified to do. Notice that if this is the third root of something to the third power, if we convert that to its fractional exponential form, it's 3 over 3. This is a 1. So our denominator is just going to be a y. And up in the numerator here, we want to separate them. And we end up with 8 for the number and a 9. This is a perfect square, but this is a perfect cube. And there is no perfect cube of x. We've got to put our 3 there. So our numerator now becomes 2, the third root of 9x squared over y. And there's our answer. A quick caution is, note that this is a plus b. You cannot do it this way. This is not the same. If they're the product of it, a times b, then you could do this. So that's a little technology here. Let's raise it. And all right, it's kind of converting here. We're going to do this, and let me put this on a whiteboard. Now, this is what it looks like on that page where it was somewhat cluttered. And here, looking at simplified radicals, you cannot have a radical in the denominator. So the protocol for this is we are allowed to multiply everything by 1, but if we use a value of 1 that will make our denominator be rational, that's what we're looking for. So if we multiplied this fraction by the square root of a over the square root of a, and remember this is a 1, we then get the square root of a over the square root of a squared, which is just plain a. So now this is in a simplified form of the radical. Now a more sophisticated way of rationalizing our denominator here is using, and again, we got a deep way into our toolbox here. What can we multiply this that would cause this to become radical from radical to rational without this? And we're going to use what is called the radical conjugate. And what is that? Well, it would be the same items, the square root of a, the square root of b, and that's on the top, square root of a, the square root of b. But it's the opposite sign in the middle, so this is going to be a negative here. So these are what we call the radical conjugates. Now, what do we do? Well, we're going to use the FOIL method, and the first square root of a times the square root of a gives us the square root of a squared, which just becomes an a. And the inners and outers just cancel out, and we get the a squared of b minus the a squared of b gives us a na squared of a b squared, which is just an ab. And then it's just this. So this is a method of changing the radical to a rational value and simplifying. And I'm going to clear this so we can see it, and then down at the bottom, there we are, and it works out. All right, so it's a little cluttered, but that's the protocol. All right, looking at example 10, and what I've copied this, well, now I'll put it in the whiteboard. All right, we're going to look at this on the whiteboard. It gets kind of complicated here. So there's our basic example, and what they're asking us is to rationalize this denominator. So I've written this part again. What do I have to multiply this again to make it a perfect fifth power? Well, this is 2 to the third, 2 to the second, which becomes 2 to the fifth, which is 32. So this is now a perfect fifth power. And then we have y to the second, and what I'm adding is y to the third, will give us y to the fifth. So our denominator now becomes, this is going to be 2y when we rationalize this here. Now our top, interestingly, when we multiply these two, I notice I can take x to the fifth would be our perfect fifth root. So out here we're going to get an x, and then the fifth root of everything else. A negative 4 times a 4 gives us a negative 16. And we're going to get our x that's left over here. There's an x left over, which I didn't put there. X left over there. And then y to the third is our answer for this. Now, perhaps it's a little more complicated. I'm going to show you that work, but this should be our answer here. Let's check it out. And bring it down a little bit here. Now, as I note the answer here, and I'll go back to the whiteboard, I see they are taking this negative x out of here. It could have been a negative, and I would think this would be okay either way, that this could be then a negative x, and this could be a positive here. Taking the negative x out of there, because of the fifth root, we could have a negative that we could take out for the x. Okay, let's go on to the other two now. And these are sort of a challenge. And now looking at B, and what I'm using is my radical conjugates in the form of 1. Here's one of the conjugates, here's the other. Now when I do this FOIL, I get square root of 7 times square root of 7, square root of 49. Square root of 49 is 7. When I do my outers, I get the negative square root of 9, which will then be a negative 3. So my denominator here is going to become a 4. And I'm going to multiply the 4 times the square root of 7 minus the square root of 3. But notice there's a common 4 here. So the 4's will cancel out. So my answer then for this is the square root of 7 minus the square root of 3 as an answer. And let's check it out. Go from our whiteboard, and there it is. And this is the protocol. All right, let's go on. Now, here is example C on the whiteboard. And again, we're allowed to multiply any fraction by 1. So anything divided by itself is 1, and this would be the radical conjugate. Oh, we want to get that, keep that here. There we go. Okay, so what does this equal here? Well, our denominator is going to be 25 minus x. And our numerator is going to be a negative square root of 5 times 5. So we'll write this negative 5, distributing this, and then a negative 5, the square root of x. And I believe that would be the answer. Let's check it out. Oh, this is a long video here, and there we go. That looks good. Okay, we're almost finished though. Now, in example 11, they're going to rationalize the numerator. So it's just using the conjugate of our top as a this over this, and it simplifies to this. And I'm going to let you either just copy this down or pause for a moment. Hopefully you can follow the steps. Okay, a few more to go, but still some rather challenging examples. This is example 12A. Let's go to a whiteboard here. And as we look at it, let's see what we can do. We want to simplify these fractions. So a negative 3. Now, a perfect square here, and what's left over would be 4 times 2, x to the 4th, and this would be 2x left over from this term. And then from this term, we get a plus the square root of 9 plus or times the square root of x. So we're 2x, I should say. There we go. All right, so this part here is a common radical. So this gives us the square root of 2x there. This is going to become a 3. And here we get the square root, let me put it this way, negative 3, the square root of 4, which is 2. Let me erase that. Two x squared that I have to put in absolute values, and then the square root of 2x. So simplifying this then, this is going to become negative 6, this part, the square root of, or the absolute values of x squared, the square root of 2x plus 3. I believe that's as far as we can go. Let's take a look at the regular screen and see what shows up here. Yes, there it is right here. Again, there's some pretty challenging material. Let's go on. And I should add to example A that we could factor out here the square root of 2x, which they've done, and then put this 3 and this part in a parenthesis. Again, there we go. So looking at this then, we want to tease that apart, and the same thing here. Now the perfect square factor of 50 is 25, and then the x squared, and then this is a 2. And here we're going to get a 2 here, and this is 27 x to the third. Okay, so I teased this apart into a perfect cube, and what was left over. X to the third is a perfect cube, and I tease that. So here I'm going to get 3x, the cube root of 2, plus 5x, the square root of 2. Now, since these are cubed and square roots, we can't go any further than that. Let's go back and see what we see here. And there it is. Now, for this x squared, we have to put that in absolute value, because it could have been a negative value there. Some teachers may accept it without the absolute signs, but that's the way they've been going so far. Okay, there's example C now. Let's go to our whiteboard and see what we can do to simplify. So we know the square root of 1 is 1. And the square root of 12 from an earlier lesson is the square root of 4 times the square root of 3, which then becomes 2, the square root of 3. So that's what we have there. Now, the square root of 25 is 5. And the square root of 48 is the square root of 16 times 3. So this is going to be 4, the square root of 3. Now, when we do our subtraction here, the book is showing one way. I'm going to show you another way too. I think maybe a little easier. That these are not like denominators. To make this a like denominator, we have to multiply this by a 1 in the form of 2 over 2. So now our numerator here becomes 2, and our denominator becomes 4, the square root of 3, minus 5, the square root of 3. So when I do that subtraction here, I'm going to get negative 3 on the top over 4, the square root of 3. Now to rationalize my denominator, I have to multiply it by 1 in the form of 3, square root of 3 over the square root of 3. So this becomes now a negative 3, square root of 3. And this is square root of 3 times square root of 3 is square root of 9, which is 3. 3 times 4 is 12. Now I can take out a common 3. There's 1 out of there and 4 out of there. So my final answer should be a negative square root of 3 over 4. And let's see how we did here. Negative square root of 3 over 4. Wow, some challenging material. Now, I hope fortunately we went over rational number exponents, that is fractional exponents converting it one to the other. So we can kind of go over this background material. Let's go on to the next example. We want to simplify this, so we're going to take that to the denominator as 27 to the 2/3, and now convert it to its radical form, the third root of 27, and we can use the exponent to the second power. Well, third root of 27 is 3. 3 squared is 1/9, then is our answer. Wow. Okay, let's go on to the second one here. Clear this up, and we get the 9th root of a negative 8 x to the 6th power. Now, for something like this, and I guess these are challenging, we can think of negative 8 as negative 2 to the 3rd power over 9, and the x to the 6th over 9. That's what this stage is showing. Now, when we put this is going to be a negative 2 to the 1/3 power, and this will be x, and this is in parentheses actually, to the 2/3 power. So we can simplify this then to the 3rd power of a negative 2 x to the 2nd. Ooh. And again, you could put that negative sign outside there, and then this would become a plus. I guess that's the way they're doing it, and we'll follow that protocol. Now for letter C, to save time, we see our bases are the same, so we're just going to add our exponents, and when we do, we get the sum of these fractions is a 6/3, which then reduces to squared. So hopefully something easy using the product rule. All right, let's do letter D. Now again, if we convert this, it's going to be basically the 3 times 5 is 15 x to the 2nd. And that's using this rule where we just multiply our index numbers here. And this one, we're going to bring this denominator up to the numerator as a, remember there's a 1 there. Subtract that from the 1 and get a 4/3. The opposite of a negative. Let's check that out a little more. It's kind of tiny, so we're bringing up a negative 1/3 becomes a positive 1/3. That's where we get the 3/4, and this would be the answer. All right, now we're almost finished. One more slide. So this is example 14. And this is like 6 weeks in a normal algebra class that we're doing in one lesson, so lots of stuff. But we're going to convert this to its fractional exponential form. So this will be x to the 2nd over 4, which is x to the 1/2, which is the square root of x. And what do they have here? Yes, the square root of x is right there. All right, clear that up. And now we have example 2. The 3rd root of 2 times the square root of 3. Well, in its fractional exponential form, this is going to be 2 to the 1/3 power times 3 to the 1/2 power. And when we multiply that, we get, let's move it down a little so we can see. And this is our final example, gets to be quite tricky. So we have this. Now we can get common fractions here by making 1/3 2/6 and 1/2 3/6. And now we can factor out this 1/6 here, and we get 2 to the 2nd, 3 to the 3rd, When we multiply this, we get 108 to the 1/6 power, which is the 6th root of 108. Wow, lots of stuff here. And I know this was long, but background for our work that we'll be doing. Hopefully the future lessons will be a little shorter. More carefully here.